So we are continuing with the C10 module using resources, and we're thinking about continuously about how we can work towards a more sustainable future. Today we are looking at a Nobel Prize winning reaction, the Haber process, and making ammonia, which was really important in fertilisers and so feeding the world's population, which I'll link with sustainability. Now, looking at this equation, we can see there are double-ended arrows which show that this is an equilibrium reaction, and this links back to the work we've done previously on Le Chatelier and equilibrium. Now, just to recap a bit on LCP, and you'll find another PowerPoint on my channel on this if you need to revise it further, but Le Chatelier worked with shifting equilibrium, so we can manipulate the conditions to make more of the reactants or the products, because basically when the conditions are changed, the system will do anything to counteract that change. For example, if the temperature increases in the system, it's going to want to decrease, so it will favour the endothermic reaction to lower the overall temperature of that system. If you increase the concentration on one side, it's more likely to make more of the stuff on the other side of the equation to bring it back to equilibrium. And increasing pressure will favour the side of a small number of molecules, because the system wants to decrease the overall pressure. So if you decrease the number of molecules, that will decrease the pressure. So to summarise those rules we've come across before, increasing temperature favours endothermic reactions, increasing pressure favours the side with fewer moles, increasing concentration sends the equilibrium to the opposite side, and if you decrease the concentration, send the equilibrium towards the same side that you're decreasing. And remember, addition of a catalyst does not affect equilibrium. Equilibrium is just met quicker, but it speeds up both the forward and the backwards reaction. So back to the Haber process. So let's have a look. We are reacting nitrogen and hydrogen to make ammonia. So where do we get the nitrogen and hydrogen from? So nitrogen is from the fractional distillation of air, and hydrogen can be from natural gas, so methane, and also from electrolysis of water. So why is the Haber process so important? Well, plants need nitrogen to grow, and they get this from soluble nitrates in the soil. But when we harvest plants, that nitrogen isn't automatically returned to the soil, so it needs to be replaced by fertilisers. And we use the ammonia to make nitrate-based fertilisers to replenish the soil. Previously, before we had this process, we would be using various animal feces, guava. The UK and Europe would have been importing large amounts of bird poo from South America to meet that need. So the Haber process, what are the conditions when this reaction happens? These are conditions you are expected to know as triple scientists. You need an iron catalyst, high temperatures, which is 450 degrees Celsius, and a high pressure of 200 atmospheres. Now, we can see it's a reversible reaction. We've mentioned that already. So we're always going to find in this reaction a mixture of nitrogen, hydrogen, and ammonia. So how do we get pure ammonia? Ammonia has a higher boiling point than hydrogen and nitrogen. So the reaction mixture is cooled, and so the ammonia will condense first and can be tapped out. So we said the ammonia is collected, but the hydrogen and ammonia gases are recycled back into the reaction vessel. This is an industrial process. It's all about being efficient, minimising waste, and making the most of your resources. So we can kind of see this in a flow diagram here. We can see our nitrogen is sourced from the air and hydrogen from natural gas. That is quite a common 1-2 mark question, identifying sources of the nitrogen and hydrogen. They're mixed in a ratio of 1:3, and that's what you would expect, because if we look at the chemical reaction, it's 1 mole of nitrogen reacting with 3 moles of hydrogen. It goes into the reaction vessel at 450 degrees Celsius, 200 atmospheres, and has an ion catalyst present. We can then see that the gases are cooled, so the ammonia turns to liquid and is tapped off, and then the unreacted gases cycle back in. So if you're in my class and have been set this as a piece of work, you will have a copy of this worksheet. So please complete this. You can go back and rewind the video if you need to find all the answers. They are all there for you. So we have talked about Haber process being a compromise before when we looked at our equilibrium module earlier in the year. But the big thing to realise, being an industrial process, that this is an ongoing compromise. So let's have a look at this reaction. So we have nitrogen plus hydrogen making ammonia. The forward reaction is exothermic, the reverse reaction is endothermic. And we've got a graph here showing what yield of ammonia we get at different pressures and at different temperatures. So pause the video and have a think about what the effect of the pressure is on the rate, temperature, and their impact on equilibrium too. So when tackling these kind of questions, we've got to realise that the rate of reaction is different to equilibrium. Rate of reaction is all to do with the likelihood of successful collisions. Okay, so looking at pressure, increase in pressure increases the rate of reaction, because what happens when we increase the pressure, we have more reactants in a given volume, and so the likelihood of them coming into contact with each other and colliding is increased. So the likelihood of collisions increases with increased pressure, so the rate of reaction is faster. When we increase temperature, we give the molecules more kinetic energy, so they are flying round and more, and so they are more likely to collide, and when they do collide, they are more likely to collide with a sufficient or minimum amount of energy or activation energy so that those reactions are more successful. So both increased pressure, increased temperature, increase the rate of reaction. But this is a reversible reaction, and so the impact on equilibrium is really important. So if we look at pressure first, increased pressure favours the side with fewer moles. In this reaction, on the left hand side, we've got 1 mole of nitrogen and 3 moles of hydrogen. So we've got 4 moles of substances on the left hand side, whereas on the right hand side we only have 2. So if we increase the pressure, the equilibrium is going to favour moving towards the products, moving towards the ammonia. Equilibrium will shift to the right hand side. Okay, and we can see on the graph, as we increase pressure, we increase our yield of ammonia. Now temperature, in this reaction, the forward reaction is exothermic, the reverse reaction is endothermic. Increase in temperature favours the endothermic side of the reaction. So that means if we increase the temperature, even though it increased the rate of reaction, we're going to make more nitrogen and hydrogen than we are ammonia. And if we look at our graph, we can see that our highest yields are at the lower temperatures. So the Haber process is an ongoing compromise by industry, and they've picked this point of 200 atmospheres and 450 degrees Celsius. So if we talk about the pressure first, ideally we would have it at 400 atmospheres or higher even, but it is really expensive to maintain very high pressures. You need stronger specialist equipment to withstand those pressures, and also more energy is required to compress those gases. So the compromise is 200 atmospheres, so low enough to keep costs manageable, but high enough still that the yield is acceptable. And then at temperature, ideally we would have it as low a temperature as possible, but if we have it at low temperatures, it is ridiculously slow. There's demand for the product, industry want to get the product quick, so they go for a temperature of 450 degrees Celsius as being low enough that the yield is still okay, and high enough that it's happening at a quick enough pace, it's being produced fast enough for them. So the Haber process, an ongoing compromise. So if you're in my class, you have been given the following questions on a worksheet for you to complete, please. Those questions are: question 1, ammonia is produced industrially using the Haber process. The reaction is reversible. So 3 hydrogen molecules plus 1 mole of nitrogen form 2 moles of ammonia. A. The forward reaction is exothermic. If the temperature is increased, what will happen? Explain why. And then B. What will happen if the pressure in the system is increased? Explain why. Question 2. Which conditions produce the highest yield of ammonia? So use the graph to help you answer this. In industry, the actual conditions used are a temperature of 450 degrees Celsius and a pressure of 200 atmospheres. What percentage yield do these conditions give? Again, use the graph. Why is the optimum pressure of 400 atmospheres not used in industry? Why is a higher temperature used when a lower temperature produces a higher yield? What else is added to speed up the rate of reaction? And you can find the answers to all these questions in the video.